Good morning, everyone. Thank you for joining us. My name is Bhushan Gopalani, and I'm a professor in the Department of Chemical and Biological Engineering at the University of British Columbia. It's my absolute pleasure to welcome you all to the session on AI in manufacturing. I'll be chairing the session along with Delaram Benami, a senior PhD student in electrical and computer engineering at UBC. We have four excellent speakers lined up for this session. Each speaker has 15 minutes for their presentation. If they finish early, you can ask them questions. Otherwise, please hold on to your questions until the end of all the presentations. Type your questions in the Q&A box at the bottom of your Zoom window, and I will read them out to the speakers. You will not be able to ask questions directly using your audio. So without further ado, let me introduce our first speaker, Dr. Greg Stewart. Greg Stewart's interests are in developing and deploying advanced control and machine learning technologies to solve industrial problems. He's currently working as a vice president for data science at a startup called Ecoation. They're developing and productizing analytics and automation for agricultural applications, including the collection and analysis of spatiotemporal data for production, microclimates, pest and disease, and crop work to find and fix problems and to optimize crop performance. He received a BSc in physics and a master's in applied mathematics from Dalhousie University and a PhD from University of British Columbia in control engineering. Greg?
Okay. All right, well, thank you very much, Bhushan. And also thanks everyone for having taking some time to listen to me this morning. Why don't I switch this into presentation mode, and hopefully this all goes well. Just let me know if that still looks good.
Yeah, looks good.
Yep. Okay, so in a few minutes this morning, what I really wanted to do was to kind of give you guys an overview about what it is that we're trying to do with AI and really start from what problems we're trying to solve for agriculture, and then how the various techniques can fit together in this one, right? We end up solving a broad array of problems here, so there will be a different set of techniques that we talk about, but really this is a kind of a picture of a commercial greenhouse that I want to start with. Just to give you a sense of what the scale of the problem is. So let's take a look at this. I'm about 3 meters up in the air. This is a tomato crop in a greenhouse. But just to get a sense of the scale of this place is pretty impressive. People say that you can kind of see the curvature of the earth inside one of these greenhouses, but it's absolutely massive, right? So these are dozens of acres that people are growing their crops in modern greenhouses. So really, what our problem that we're looking to solve here is, can we find any important anomalies about what's going on within this crop, and can we assist growers to find and fix problems? I mean, as you can imagine, right? I'm driving a cart down the road here. I can take a look at the plants that are near me, but keeping track of, is there a problem, over here or one over there is an extremely difficult problem for an operation of this scale, right? And so what we want to do is to try to get a sense of what it is that we can help the growers with in this case, right? So to get started, oops, I need to be able to shift one slide instead of starting the video. There we go. So just kind of quickly here, the platform that Ecoation as a company has developed is this cart that you see here, right? And well, at least the cart is where we locate all of our sensing and instrumentation, right? So these carts are driven within a greenhouse during what they call pest scouting operations, where somebody will typically scan or go down every second row of the greenhouse once a week, and they're checking for pests and disease on all of the plants and recording this. And sometimes that's recorded on pieces of paper, and more recently electronically, which is far superior for reasons that probably don't have to explain to this crowd. But really the robot that we have it's instrumented with cameras, which I'll talk about kind of next, some climate sensing, the temperature, humidity, CO2, and the light, and then expert human inputs, which are used for when people flip over a leaf and they notice spider mite and they want to write down where in the greenhouse the pest problem has started, right? So I'll talk about that now. Now, the first thing that the greenhouse does, it's really its primary job is to produce something, right, and sell it. In this case, we spend a lot of time in tomato greenhouses, and a row may be about 200 meters long, and there's tomatoes all the way down it, right? So if we want to ask ourselves, how much is my crop producing? And even harder, where in that massive greenhouse are my underperforming areas? This is a pretty tough question. So what we have here, I'll just do another video if I can make this work. It's a computer vision solution, and I won't explain the model just yet. Just look at the video, and you can see that as we're rolling down the row, this one is showing you the bounding boxes around the fruit. So what we're able to do is to count these things automatically in the entire row and know where they are. So for example, if you're getting less fruit produced at the back of the row than up at the front, this is an interesting piece of information that the grower can use and perhaps adjust the airflow throughout the greenhouse to get a better, get to change to make it more uniform. The model that we're using here, just quickly, in order to get it to work, we had a third party draw bounding boxes around 30,000 tomatoes. And this is from our own cameras in our own greenhouses, right? Or I should say our customer's greenhouse. So this is not labeling off the internet. So we train the model. It's a YOLO V3 darknet with 24 layers. If there's questions, I can answer them at the end. I won't go into too much detail here, but really what we're doing is counting and classifying the tomatoes according to their ripeness. So you can see, I don't know if you can see it here. Some of them are red, some of them are green, but understanding how quickly they're moving from green to red is another interesting problem that we can start to help solve. The problems with this include occlusion, what speed somebody feels like driving the cart at, the angle, meaning, if I've got the cart up high, I don't have a great angle to look down at the tomatoes, so you need to get that right, and then figuring out the color, right? So these are things that we needed to address in order to make this work in production under all conditions. Now, again, each time I click, it does this. Pest and disease, this one is really interesting. And really what we're trying to do is understand where are my pests in the greenhouse and where will they be next, right, is even a more important problem. You can see a typical map here where you have the pests and you can see how they're distributed in the greenhouse. And you can see these guys, there's kind of a hot spot here and maybe a few others, and then a lower amount of pressure at these other areas. But what will end up happening is these things tend to spread over time. So if you don't get on top of them and know where they are, it can take over the greenhouse and wipe out your crop. The bios is something which is related. These are the good bugs that people buy to go in after the bad bugs. And so you can avoid using a lot of chemicals if you are on top of your pest pressure and able to distribute the biological controls ahead of time, right? So models for this, what we're doing is really, these are very different than the ones I just talked about. This is a spatiotemporal projection based on the sparse observations, which really means that as the scout goes down the row and marks where these pests are, what we use that as an input into these SEIR type models, which are very similar to how people are projecting how COVID propagates throughout the population, right? And so we can project where the pests are going to, or are expected to go. Now the challenge here, there's high uncertainty in biological agricultural systems. Sort of my early part of my career was spent on things like paper machines and diesel engines, where it's really physics and chemistry which govern a lot of what's going on over there. In agriculture, you really have to have respect for the biological uncertainty that comes along with it. Okay, next. When we talk about climate, this is the other thing. Now, usually in a greenhouse, you'll get a climate sensor. These are climate controlled environments. In fact, that's why you have a greenhouse instead of being outdoors. But they'll have one climate sensor which measures CO2, temperature, humidity, usually every few acres in the greenhouse. Now, if we're driving our robotic cart up and down the rows, we're able to map out the climate on a per meter basis within the greenhouse. And then you can start to discover interesting things like this. This is a humidity map at the top, and you can see that close to the walls of the greenhouse, and I'll show that, it tends to be drier than these areas out in the middle, right? Now, the thing that we notice then, if we combine that with our pest maps, we also see that that there's a correlation between the moisture as well as the pest pressure. And so then this will in turn potentially have an impact on your production. So this is the type of thing that you can start to see if you start to bring together these measurements that we've never really been able to do within agriculture before. Now, one of the challenges here, and I won't go into a ton of detail, is that the climate throughout the course of the day, it's cold in the night, and in the morning, it reaches a peak around 4 in the afternoon, and then it drops off again. But you don't drive your cart around exactly every row with every minute of the day. So you've got to be careful and figure out a data-driven way to, let's say, if I visit this area at 9 a.m. and I found that it was, can I say whether that is abnormally warm or abnormally cold? I've got to understand something about the spatial distribution as well as how the whole thing changes over the course of the day, right? That was harder. You get this kind of, if you don't do it right, you get this kind of spatial aliasing, which is really fascinating, but I don't have a lot of time to talk about it here this morning. The next thing is what we'll kind of generically call crop work. Tomatoes are what you call an indeterminate crop, meaning that they'll just keep growing, right? So they can become as big as 10 meters high by the end of the season. So what they do is every week they want them to be at the same height because of the producing part of the plant is really only at the top. So they will lower them. They grow, let's say, about that much every week. So they want to lower the plants and slide them along. So wherever you see a plant, its root, so the root of this plant may be way back over here someplace, way down in the ground, which is really interesting. So now, as you're moving the plants along, there's all kinds of things that can go wrong. People can space them badly. People can break the heads. These things really have an impact over the crop. So the next thing that we're doing is using a vision system, get rid of my drawings here, to detect where the stems are in the picture. And I don't know how good the quality is here. I swear it's better on the camera itself, but we're able to detect where these stems are. And what we want to be able to do is to find anomalies in this. Did the density of the stems get too high? Are they packed too close together? In which case that they'll be shielding each plant from one another and the photosynthesis will be compromised. So this can start to contribute also as well to understanding what's going on in the crop. And then I guess finally here, this is where I wanted to try to get is that all of these things are important together and in fact more, right? So if I want to understand how to optimize the production in my greenhouse, I really do need to understand the interaction of all of these things, right? Say the yield of the tomatoes, the pest pressure, it's called IPM here, which stands for Integrated Pest Management, the crop work and how well that's being done, along with the climate anomalies. So through, and my bigger point here is that all of those models that I had, all right, everything from the epidemiological model for the pests to the vision-based models to the basic analysis of the climate, ends up getting combined together, right? So we end up with these, what you're looking at here is map of the greenhouse, a map for the fruit count over here on the left, then you have the stem count, then you have your pest pressure, and then you have your climate. And what we're working on now is to be able to link these things together. So if I find, for example, an area where my tomato count is lower than the average of that greenhouse, I want to see really what else is going on there, right? Is there something going on in the crop work? Is there something unusual happening in the climate? And what we can get people more or less immediately is the ability to be able to find and fix problems, or at least come up with a short list of things to look into. If I've got a depressed fruit count and I don't have a pest pressure problem in that area, then I don't have to go and try to buy more biologicals or do a spray. I may look at the climate if that's the place where the first anomaly is, right, to try to correct these things. So what we're really trying to do is to get this sort of overarching view of the greenhouse so that we're able to start to understand these problems from a more data-driven way and to try to connect all these things together. Now, some of the mathematics that'll go into this activity here is actually, it's interesting. It's related to very old ideas from manufacturing that I used before when I was doing some carbon fiber brake manufacturing work, where you're looking for anomalies in the process, and statistical process control, especially applied to batch processing, has a surprising amount of applicability to the greenhouses if you consider, now you won't have the same conditions in a greenhouse in agriculture week after week, but what is supposed to be the same is the spatial characteristic of it. So every spatial zone in the greenhouse you can consider as its own individual batch, and if these two zones across all of these parameters are behaving differently, then you can start to understand something about the what you can do to make things better for the grower. Okay, I want to stay under my 15 minutes, so I'll stop there. Happy to take any questions if there's time left. To be honest, I've lost track of that, so I have no idea whether I can take questions or not. I'll leave that to Bhushan.
Thank you very much, Greg, for an excellent talk. Let's just move forward because we started a little late, and we'll have 15 minutes or more later at the end of this session for questions. There are no questions yet in the Q&A box, but we'll have time at the end of all the presentations. So let me introduce our next speaker. It's Professor Anoush Poursartip of the University of British Columbia. He is a professor in the Department of Materials Engineering. His main area of research is polymer matrix composite materials. The two most important areas of concern with the composite materials are damage growth in service and processing science for efficient manufacturing. He has been involved with both of these topics, important topics, using a closely coupled experimental and theoretical approach. His research has spanned a wide range of topics as he has tried to develop a global appreciation of the issues facing composite materials. Anoush?
Thank you very much, Bhushan. Thank you for this opportunity to talk to you about AI and advanced composites manufacturing. And I really appreciated Greg's comparison between the food industry and manufacturing in general. Manufacturing, of course, being the transformation of a raw material into a more finished product. Manufacturing is difficult, and the best person to say this to us is none other than Elon Musk, who, as we all know, has created a revolution in electric cars, but in doing so discovered that manufacturing is really quite difficult. And he's come out and openly said that the difficulty value of manufacturing is underappreciated. In my case, I work in an area where manufacturing is really, truly difficult. And that is, we work in the area of fiber reinforced advanced structures using carbon fiber. It's the strongest, stiffest material available. And a single carbon fiber, it's about 5 microns in diameter. We literally take billions of these fibers, put them together in a gooey mess, the matrix, and we basically got double-sided sticky tape. And what we do is we use this to actually additively make very large, complicated structures in essentially one step. So the way we do this at the advanced end of the business is we use very sophisticated robots which lay down strips of this material on a very complex mold, and we build up whatever structure we want. So we can build up literally a whole airplane wing in one step. What we then have to do is literally cook it. And so your mental image of cooking lasagna in an oven is absolutely applicable. What we have is these huge pressurized ovens. We roll in the tooling and the part, and we cook it. And we have to cook it right. And one of the difficulties is that we have to ensure that we get the right temperature history. And that gooey material that turns into a solid polymer, that actually, when it cooks, is exothermic. It puts out heat. So initially, you're trying to get the heat in, then you're desperately backpedaling, trying to get the heat out. If you get it right, what comes out of this are structures that have actually revolutionized aerospace and wind, for example, and increasingly affecting other industries such as automotive. So if you look at, say, the Boeing 787, and of course, we'll talk in a moment about the woes of the airline industry, but the 787 is an all-carbon fiber airplane, both the fuselage and the wing, as is the Airbus A350, which are the two leading airplanes in the world right now. The Bombardier C series, now the A220, has a composite wing as well. And if we look at energy, The revolution in wind energy has been made possible by our ability to build these astoundingly large wind turbine blades. Again, the thing that holds us up from going even crazier is manufacturing, design, and control. It's one thing to design it, as Elon Musk said. It's a totally different story to actually make it well. And so the potential is vast if we can overcome the difficulties. So this, of course, brings us to digital manufacturing. And this, of course, has been around for a very long time. And those of you who know the industry jargon know that we are at the dawn of Industry 4.0, where people are talking about all these things, the Internet of Things in terms of sensing, AI, putting it all together into embedded systems. The key point to make is that the kind of manufacturing that is important to, say, aerospace in composite materials requires us to actually think about the science of what we're doing. And you'll see why in a minute. And again, this goes back to some of the comments that Greg made. And so we really need to think about how science has evolved over time. And if you look at sort of a comparable history, we started off with empirical science. We moved to model-based theoretical science. And in the last couple of decades, computational science has been the rage. And now, of course, what we're doing is we're saying, hey, what does it look like as we bring it together with sort of the data-driven approaches, and we get into this world of integrated computational materials engineering. And in recent times, there's been lots of talk about what our people are calling scientific machine learning, scientific AI. So again, let's remind ourselves, different sectors have different needs. And say automation has very different meanings in different sectors. You can think of it as discrete versus process manufacturing. If you think of electronics assembly, that's discrete manufacturing. It really is a matter of bringing the right pieces together. It's a logistics problem fundamentally. But if you look at, say, an orange juice factory, that's a process engineering issue, and you're actually trying to understand the transformation of your raw material. If you want to think about just bringing classic AI to bear on the problem, you really have to think about how much data you have available for training. So looking at three markets with roughly the same commercial value, if you look at Apple, 140 million iPhones a year. If you want 1 million data points to train your algorithms, that's about 2 days production. If you look at Toyota, who build 8 million cars a year, well, they'll last for 6 to 8 weeks to give you 1 million data points. But if you look at Boeing, who build less than 1,000 airplanes a year, they'd be looking at 1,000 years to give you 1 million data points. So clearly, the AI approaches you're going to use in different sectors has to be really quite different. The other thing that is really different in some sectors, especially aerospace, is that safety and regulation can impose really severe requirements on the use of technologies such as AI, but even classic numerical simulation. The expectations of accuracy. We design to a 1 in a billion failure rate. We're unhappy if our failure rates drop below 1 in 100 million. We have to show explainability and causality in everything we do, and we have to have astounding traceability in everything. So to succeed with Industry 4.0, and this is, of course, a topic of much discussion, is really, I would argue, 5 core enabling technologies that you have to integrate. And the way I present it is perhaps a little bit different to the way other people do it. Automation. Clearly, at the end of the day, we're trying to automate everything we're doing. Clearly, sensing, Internet of Things. Here, of course, we can use all the technologies that exist out there. Again, Greg showed some examples. We then get into the world of data science, including AI. I like to unpack out of that uncertainty quantification. And the reason I like to do this is because this then gives me a bridge to scientific process simulation, which is the state of the art currently in terms of what we have done to bring digital to manufacturing. And the key thing is that we really need to bring all these technologies together in a very coherent manner so that we can use them all the way from design, because your biggest decision is building the factory, through to actually production for sometimes decades. So at the moment, the baseline is physics-based numerical simulation. So if you look at, say, the Boeing 787, this was designed in the 2000s, and the manufacturing cycle for this airplane, remember, this plane is all carbon fiber epoxy. Boeing actually used software written by 2 UBC students, which was commercialized through Convergent, to actually design the manufacturing cycle for the airplane. At this stage, the autoclave, the tooling had all been built. So the only thing that could be optimized was the actual manufacturing cycle. Fast forward 10 years, and Boeing actually had the luxury of designing the whole autoclave, basically the factory, again, using numerical simulation. Now, these models are incredibly computationally expensive. And so as we start saying, how do we merge science-based simulation, where we have lots of confidence, lots of background with data-driven modeling, we have a wide range of methods that we are evaluating, physics-inspired neural nets, all sorts of other methods. The one I'm going to show you very quickly today is called theory-guided machine learning. And in theory-guided machine learning, what you're trying to do is live with the fact that you have small data sets. And again, I want to remind you that our data sets really are very small and very expensive. So what we basically do is we bring to bear any physical data we have. This would be sensors in production. It'd be offline experiments. We have domain knowledge. Some of that is explicit in the sense that it's very simple equations, very simple relationships. It can be know-how captured in mathematical form, or it can be numerical data. It can be high fidelity 3D models, which are superbly expensive. It can be fast simulations. But what we do is we take those and we basically use them to create surrogate models. So we use all of that to create physics-based feature transformations, physics-based layers. We can go with smaller neural nets. And just to give you a quick example, if I'm trying to cook a thick part on a tool, again, think of a big roast for Christmas in your oven, then what you're trying to do is create a surrogate model, and you're trying to predict how much this part will overheat. So you would plot the exotherm, the amount of overheating versus the heating rate. How fast are you heating your oven? In the training zone, if your ground truth is your numerical simulation, a classic machine learning algorithm replicates numerical simulation just fine. The value of a theory-guided approach comes if you try to use the model outside the training zone. Now, the physics ensures that the theory-guided machine learning behaves well, whereas the machine learning algorithm breaks on you. The value of these kinds of surrogate models comes out when you try to, for example, do optimization. We're always trying to shorten the cooking cycle, the cure cycle for our products, because they can take a very long time. So if I compare, on the left, I have direct finite element numerical modeling. On the right, I have a surrogate model. In both cases, I'm controlling the air temperature in my pressurized oven. That's the cyan line, to ensure that the part temperature, the purple line, doesn't go crazy on me, and I keep it within the bounds. And I'm trying to cook the material, which is shown by the yellow lines. If you did no optimization for this part, it would take you about 400 minutes to cook this part. Both methods give me a very optimized cycle of about 117 minutes. The big difference is that the numerical modeling takes 14 hours. The surrogate model takes 90 seconds. And yet that surrogate model, we know, is well behaved. So a really nice example of how I end up getting the best of both worlds. So to summarize, manufacturing, like all other aspects of life, is being disrupted by digitalization. And within that, there's a huge effort to bring AI to bear. The key point is that the processing component of manufacturing must obey the scientific laws of chemistry, physics, mechanics. And this is a ground truth that we must observe. And so in that sense, it's an imposition, especially when we have the very high safety requirements that we do. But actually, it's a benefit because it gives us a systematic backbone that we can exploit. And so the fusion of sort of deterministic engineering, numerical simulation with AI, which I'm one of the people who likes calling this scientific AI, really provides an exciting avenue. And it's an opportunity for both research, but actually value creation. A little bit about ourselves, the Composites Research Network at UBC. We're collaborating very closely with the Data Science Institute under the leadership of Dr. Raymond Ng. We're getting our funding from industry, from the Digital Technology Supercluster, and of course, NSERC and UBC. And colleagues who are composites experts are working with folks like Dr. Trevor Campbell, Dr. Frank Wood, Dr. Humayun Najaran. So I am for sure not an AI person, but I've made it my mission to make many, many friends in the AI sector. We're also looking at this in a bigger way, looking at advanced materials manufacturing in general. We're actually even talking to our colleagues in quantum computing, offering up materials and manufacturing as an opportunity. We're collaborating strongly with the German Aerospace Center, who have very similar interests. And of course, like many others, we see huge opportunity in this area. With that, I believe I am done, and I'd like to acknowledge that everything I'm presenting is, of course, the work of lots of people across the board, in particular, Dr. Joran Fernlund and Dr. Reza Vaziri. And of course, I'd like to acknowledge funding from the Canadian government, the Boeing Company, and other industrial members of the CRN. Thank you very much.
Thank you very much, Anoush. That was an excellent talk. So we'll wait for the end of the presentations for questions. Let's move on to the next speaker. Our next speaker is Kalev Ruberg. Kalev is the Chief Innovation Officer and Vice President Future at Teck Resources. Kalev has held the position of CIO with Teck since 2006 and has a long background in information systems, technology, and applied artificial intelligence. Most recently, Kalev was appointed VP Future and Chief Innovation Officer, where he's exploring the future of mining at Teck. In 2020, Kalev was also appointed Adjunct Professor at the Keyville School of Mining Engineering at UBC. Kalev?
Yes, well, thank you very much. And it's a pleasure to be here, at least virtually. And thank you again for the speakers. An incredibly interesting work being done both at UBC and in BC generally. I'd like to really refer to Soren Kierkegaard on this. And life can only be understood backwards, but it must be lived forwards. And I think Anoush certainly demonstrated some of that principle. And mining is an interesting or a very different kind of industry. I do want to actually also inform everybody that this is forward-looking information, and it may be materially different from any future results, as we all know. So Teck Resources is Canada's largest diversified resource company. We have an interest in 11 mines in the Americas, both North and South America. We're the #1 producer of steelmaking coal in North America, #3 of zinc in the world. Certainly sustainability is a key component of our strategy and of our operations, and safety is paramount. So visions of the future. And you would not believe how many people try to actually find out where this mine is. They have all kinds of suppositions about it, but of course this is a Hollywood rendition of what mining is about. There's certainly no intelligence here. And as you can see, the machines get bigger and bigger as time goes on. This is from the year 2154 on a planet far away from Earth, 4 light years away, apparently. And as you notice, the trucks haven't changed. The mining equipment really hasn't changed. And I'm not really sure how they got this, 400,000 ton machine to the other planet when they can barely get people there. But that's Hollywood, and the reality is quite different, because most mining CEOs and most mining executives are concerned much more about sourcing responsibly, about social license and community engagement, about the environment, about our employee engagement, and certainly about the environment itself and the culture and the employee and the employees that work there and the communities around us, as well as regulatory compliance. And if you look
Excuse me. Sorry, Kalev, sorry to interrupt. Just want to make sure, are you changing the slides? Because we're only seeing slide 1.
I am changing the slides.
Okay, it's probably the wrong screen that's being shared.
Can you see these now?
Didn't change.
Interesting. Okay, well, I'll stop sharing for the moment and let's see if we can try it again.
Mm-hmm.
Can you see it now?
It's not in presentation mode, but I do see slide 5.
Right, so let's put it into presentation mode here. Can you see that now?
It didn't change. It's still slide 5.
Oh,
Kalev, what you have to do is go into presentation mode, then share, and choose the presentation screen. Zoom is a bit strange that way.
well, we'll try that again. All right. And I've lost, of course, I've lost my Zoom here.
Corona times.
We're out of time, are we?
No. I just said Corona times.
Yes.
No, we're okay. We're good.
Okay. Now, how does
Looks
that
good.
work?
Yes.
Looks good.
All right. So I'll go backward a couple of slides here just to give you context of what I was talking about. And now, unfortunately, there you go. So this is obviously from Avatar. It's a picture of that huge mining equipment, and it's a vision of the future 120 years from now. Nothing has changed in this industry, and certainly no intelligence has been shown here. And so all CEOs know that this is certainly not plausible, and their current priorities and their future priorities are really quite different. And they really focus on safety and responsible sourcing. They focus on employee engagement. They focus on the environment and regulatory compliance. And in order to actually, and by the way, this is across the board, that's true. It involves ESGs. So the focus of this word chart is really to look at replacement cost, workforce future, but you'll notice that in the middle and the biggest issues are ESG, zero GHGs, and then cyber, and then also digital optimization. So that becomes one of the key words and the key methods for achieving what the industry would like to achieve. In addition, of course, we can't forget that these are businesses and they're highly functional businesses. And the whole industry is looking at a potential value of $375 billion at stake in terms of the value of digital innovation and the performance increases it brings, as well as all of the changes it brings in our ability to mine both safely and environmentally, in a very environmental way. And it's across all kinds of technologies, including advanced analytics, digitalization, automation, and across all of our supply chain, and everything from exploration through mine operations and processing, maintenance and business support functions in the supply chain. So we're looking at 11 to 16% of that 375 billion that could actually be changed. To that end, at Teck, we have a Senior Vice President of Technology and Innovation, Andrew Milner, who brought the concept of Race 21 to leverage our AI to transform operations. And when I'm talking about AI, I am talking about machine learning to a large degree on processes. And Race really is about renewing a modern technology foundation. And as Anoush indicated, it's all about getting all of the IoT sensors and the tooling right within your environment, and that's sort of what we are embarked on. a very ambitious program to automate and accelerate the scale of the autonomy program within Teck, to connect every piece of information within our mining environment, both in the operations as well as the business, and then to actually empower people to make decisions along with the machines, which is actually the most powerful mode of operating machine learning. And so it's linking disparate systems into this collaborative digital platform and increasingly getting dynamic and predictive models for dramatic improvements. Now that's not only for the business itself, but it also allows transparency to the communities that surround us and depend on us. And making it real, of course, as always, is very difficult. And immense amounts of data are needed to learn and act. We have 60 terabytes, for example, of data from trucks, 1 billion truck sensor records per day. And we have like 450 trucks around the world. But we have 91 billion records for machine learning, 260 trucks, and that's 10 years of collection. And it's not all great, clean data. And we have 440 sensors on the truck, and we process about 1,000 records a second. So as an example, we have high voltage failures in our truck that can be very catastrophic. And they can lead to about $4.6 million annually in terms of fires on trucks. And then the machine learning implication is that this kind of capability can actually be applied in very, very many places. And we found that alarm frequency analysis and pattern recognition actually was a very predictive method to prevent this cascading failure. And you'll see that picture there. There's $150,000 in failed electrical parts, not to mention the risk to people. And while we have been doing a lot of analytics and on-site analytics, the actual interface to the asset health supervisor has been quite simple. And it's ugly but useful, and it actually fits right into what they have been doing all along. And that, I think, is key, is that, do the things that people have been doing all along and tell them that this is a little bit special. And it's a little bit special because people were skeptical. The machine learning algorithm could reliably predict failures. Organizational change management was critical to the success of the project, and correct corrections helped build those confidences in skeptics, because one truck was brought into the shop when the machine learning algorithm said that there was a problem. The second problem was that when it was brought in, the technicians couldn't find a problem. At that point, the truck was sent back out. The machine learning algorithm said, there's a problem. And so they brought it back in, and they actually did find the fault. And that built more trust than anything else. And that's actually what gets systems used. On advanced haul analytics, you have increased truck productivity, increased haulage safety on all of these different roads that are not, they're not highways. And so you really do have to develop an understanding of how you increase the truck speed, how do you increase operator visibility and sight lines so that they don't actually have collisions, and increase the engagement with the field personnel as you're doing it. And there's a large payoff at the end of these, and that's what I think is really important, is that Race 21 actually is built to deliver a path to value. In other words, EBITDA to the company based on the kinds of tools that are being input into the organization. So there's a new tool for plant operators. The tool uses advanced analytics and machine learning, and it increases the amount of material a plant can produce. And you can see the targeted impact in the $45 million range per year. And it's significant. So how do we move mining to a manufacturing model? And there are very, very many obstacles to doing that still. But it's all about systemic and getting to a systems-based application of AI, and also getting out of the norm of building bigger machines all the time. So and reaching zero GHG. So this is sort of, every piece of equipment here would have AI on it. Some of it exists today, some of it doesn't yet. But it provides a path to what do we really want to achieve. And certainly applying these technologies bits at a time within the process is really helping both optimize the process as well as reducing our footprint on that process. And here you see a heads-up display actually displaying how much load is being put into that surge loader, which then actually loads the very, very small trucks. And so it's a completely different philosophy. How do you swarm trucks on a site as opposed to $10 million trucks on the site? How do you get $200,000 trucks on the site? And you can have 1,000 of these. And if they all have some form of autonomous intelligence that's above level 3 or 4, you're suddenly running, they're running the mine and actually acting fairly independently throughout. And of course, you have to, the cycle times on batteries is still fairly short in high intensity usage. And so you do have to power these things up fairly often. But it is a very different vision than the one presented by Cameron. And as indicated, every single piece of equipment within the mine requires its own independent thinking capability. Certainly, the whole autonomous work being done around the world right now on autonomous fleets would be applied here to achieve actually a zero GHG mine. But that doesn't come without that interface to people, and actually what that reimagining means is that we also have to redesign our operating model and redesign how we work throughout that entire process to achieve reduced water usage and energy consumption and copper output in some cases, as well as coal output. So there's been a constant focus on value, and you saw 3 particular projects. We've been looking at more than 90 at the same time. We're creating the tool, and that's just the start in terms of machine learning. Broadening the focus across all of our operations and understanding knowledge, water, and tailings, not only the path to value part, and also providing a systemic view. In other words, very much like Anoush said, we are now working with simulation to understand how do we optimize the outputs from machine learning. And simulation, just like Anoush said, is used because we don't actually have levels of data that are required for the next step on the machine learning curve to analyze systems. And the systemic analysis, I think, will give far greater value than just the simple machine learning on each process. And so we're basically trying to tackle all 4 issues at the same time, both safety, profitability, productivity, and cost. And that's that. Apologies for the beginning. That technology always does not quite cooperate.
No, thank you very much, Cal. That was a fantastic presentation. So we have one more presentation. After that, we'll spend 15 minutes on answering questions from the audience. So let's move on to our next presentation. It's by Mong Dang. Mong is a manager of advanced analytics with Suncor Energy. She holds a BSc in computer systems engineering and has a master's in biomedical engineering. Mong leads a team of data scientists, data engineers, and industry stream specialists with a focus on innovating with data. Experienced in image and video advanced analytics, predictive modeling, signal processing, data visualization, and machine learning, she has provided data analytics solutions for large to small-sized companies and built strategic and implementation services in technology across the globe with clients in energy and resources, manufacturing, healthcare, consumer business, real estate, and public sector. Mong also sits on the Artificial Intelligence and Advanced Analytics Working Group with COSIA. Mong?
Thanks, Sean. I just want to make sure that Teck is working for us. You're able to see my screen?
Yes.
Okay,
Thank
perfect. All right, well, welcome everyone. It's really great to virtually meet all of you who are interested in learning about the application and advancement of emerging technologies in the industry. So like Vishan said, I'm a leader in advanced analytics arm of Suncor. I started off in pharmaceutical manufacturing industry for about 15 years, after which studied computer systems engineering and mastered biomedical engineering in university. Then went on to work in consulting for 9 years, where I spent my time in different industries, energy, consumer goods, public sector. After that, I was drawn to Suncor's culture and people and have been at Suncor for 5 years. I've spent most of my time in management consulting and technical roles. When Suncor made a strategic decision to invest in business intelligence and analytics in 2014, I worked with the senior leadership team to define the strategy. Then coming out of that, we set up our first enterprise-wide analytics function. And last year, we branched off a more specialized advanced analytics business, and I moved into my current role as a technical leader in data science and AI. In our company, we have a saying, advanced analytics is a team sport. I have the pleasure and privilege of sharing our team's ongoing journey and successes in emerging technologies. So I'll start off with a background of Suncor for those who may not have that much information of Suncor, then our business evolution into what we call Suncor 4.0 chapter, where artificial intelligence and advanced analytics are key technologies supporting the innovation of our energy industry. So a little bit about Suncor. Suncor is Canada's largest integrated energy company. Our operations are focused on oil sands extraction, upgrading, onshore and offshore oil and gas production, petroleum refining, and product marketing under the Petro-Canada brand, as well as renewable energy development. We have interest in 4 wind farms across Canada, and we also operate Canada's largest ethanol facility. To understand where we're going in technology and where we're at, let's first look at where we've come from. The first bold move for Suncor 1.0 was actually from the 1910s to 1970s. It's about discovering how our Canadian oil sands could be economical. At that time, it was really a huge gamble. Suncor 2.0 was the 80s to the 90s. We made oil sands economical, made possible by new technologies at that time, like truck and shovel, and later on in situ. Suncor 3.0 was 2000s, 2010s, was about creating energy for the future. Suncor and Petro-Canada merged, creating a strong integrated business model that heightened Canada's competitive advantage globally. In our next chapter, Suncor 4.0, where we'll focus on purpose-driven, people-focused, data-informed, and technology-enabled. Purpose-driven to us means our contribution to society is clear, relevant for our company, our employees, communities, and stakeholders. People-focused is putting our people at the center of everything we do, improving our workplace, making sure our employees learn and grow, feel safe, respected, and supported to be the best every day. Data-informed stems from acknowledging our data is a valuable asset, and we have to make sure that it is accurate, accessible, and we can use it for better and faster decisions to run our business. Last but not least, we will use digital technology to create new ways of working that were never possible before. But it isn't just about the next cool new tech tool. It's about tools that help us achieve our values. To achieve those 4 targets, the Transformation Management Office was built last year to act as a catalyst for accelerating and translating this change to achieve Suncor 4.0. I will now share 2 transformational priorities that most align with the work we are doing in advanced analytics and AI. This direct strategic link from the top down has been key in advancing AI opportunities. The first transformational priority is creating value from data. By developing a focused data strategy and leveraging foundational technology upgrades and centralizing data and process governance, we will model where data originates and where it goes in a consistent way. And as we know, large volumes of good quality data is important to AI models. The second transformational priority is securing our future for using digital technology. We are not pursuing technology for technology's sake or chasing the latest shiny object. Rather, we are driving to improve in ways that were not possible before, to make our people safer, improve sustainability, reduce cost, increase reliability and productivity. My role as an advanced leader is looking at how we can apply analytical techniques, artificial intelligence, machine learning across the operating businesses, as well as functional groups. We are in the process of building an advanced analytics organization We have and continue to hire data scientists, data engineers, and visualization analysts. And we developed our strategy last year and have started operationalizing this. So what is that strategy? It's built on the following. We are business value driven by collaborating with people to identify and deliver analytical methods that drive real value. We build and sustain deep and broad capabilities by developing depth of expertise in AI that is necessary to deliver the value identified. We partner and train and embed expertise as required throughout the organization. We will prepare Suncor for new ways of working by providing the insights, tools, and expertise to change the way we work and build a community around those practices. Lastly, we will leverage expertise from a diverse ecosystem of partners by bringing in the support required to develop the best outcome. We also look at technology development to reduce our environmental footprint and cost. In 2019, we invested $830 million in technology. In the same year, we completed the first cross-Canada network of 50 fast-charging electrical vehicle chargers at Petro-Canada stations. Examples of digitalization investments are autonomous haul trucks, drones, and remote sensing. Now, I'll dive deeper into 2 examples of these investments and advancement of AI, and starting with autonomous truck systems. Autonomous haul trucks, or AHS, operate using GPS, wireless network systems, and perceptive technologies. The trucks operate predictably and employ a suite of safety measures like prescribed route mapping and obstacle detection systems. Trucks used to support Suncor operations are designed to operate in either an autonomous or manual mode. With that introduction, allow me to show you a short AHS video.
Responsibly unlocking the potential of the oil sands requires innovation. And in the 21st century, technology development and innovative thinking are key to how we do business. Accelerating the pace of innovation will increase Suncor's operating efficiency and lower our costs. This is fundamental for our long-term sustainability. Sometimes we aggressively lead research and development of new technologies, but sometimes we collaborate, leveraging and advancing the work of others. One such collaboration involves autonomous haul trucks. Komatsu has developed technology that allows safe and efficient operation between manned mining equipment like shovels, graders, and dozers, and autonomous haul trucks.
Basically, what it does is puts a control system on the truck, and then a computer control room controls where those trucks go and how fast they go and how they operate. The technology has been deployed in other parts of the world, primarily in Chile and in Australia. That's really what we've been working on for years, is to try and figure out, can we take that technology and apply it to a soft rock mine where we have snow and rain and those sorts of things. So that's been the entire focus of our efforts. And so now that we've done the work, we're very confident that we can safely deploy this technology in our environment. An autonomous haul truck needs to know 3 things: where it is, where it needs to go, and what to avoid. And there's GPS on all of the equipment in the mine, so that the system at all times knows where each piece of equipment is in space and relative to each other. So trucks only travel along predefined courses to assigned destinations. A supervisory system manages the safe movement of trucks using onboard systems and GPS information provided from all vehicles in the mine area.
AHS technology offers several potential opportunities: enhanced safety performance, better operating efficiency, lower operating costs. But moving towards autonomous technology doesn't mean moving away from people.
Like almost any technology, the technologies do have an impact on workforce. In this particular case, we change our workforce and we end up with different skills. We're helping and working through with employees on the transition of the workforce associated with this. There will be some people that will be impacted, and we're working through now as exactly how that will work.
Let me just switch over to my slideshow here. So AHS continues to be a key part of our digital transformation journey. And with full deployment, it'll be the largest investment of autonomous vehicles in the world. Another area we have applied AI techniques is in our extraction process with an AI-driven advisor. Extraction was looking for ways to improve its bitumen or energy extraction to gain insights from the data it collects to increase performance, both now and in the future. During our initial proof of concept stage, the operations team worked with our data scientists from the advanced analytics team to look at historical plant data, modeling to see plant performance patterns. The tool delivers value by enabling users to optimize to current operating conditions to increase bitumen production, while at the same time driving new learning and training for control room operators. So tying it back to what I had said earlier about analytics is a team sport. We have a long list of idea backlog, about 400 plus of AI and advanced analytics applications in our industry. And we know we are better by working with our ecosystem, both internally and externally. In the remaining slides, I will talk about our current external ecosystem and what that looks like. As of September 2020, South Korea, Singapore, Germany were on the top of Bloomberg's NEF's National Industrial Digitalization Ranking. Leading countries hail predominantly from Asia and Europe, with each region taking 4 of the top 10 slots. Canada took 9th and the United States ranked 7th. AI remains the top technology focus as countries race to establish themselves as leaders. In Canada, our government appointed CFAR in 2017, as you can see in this graph, and to lead a 125 million pan-Canadian artificial intelligence strategy, the world's first national AI strategy. CFAR works in close collaboration with Canada's 3 national AI institutes, AMI in Alberta, MILA in Montreal, and Vector Institute in Toronto, as well as universities, hospitals, and organizations in the country. Now, why is that relevant? We, Suncor, collaborate with AMI as part of our city's economic development initiatives. We're also not doing this all on our own. We're looking at how we build and support more of our ecosystem, so we raise the tide together. In 2019, we established a strategic relationship with Microsoft. Suncor selected Microsoft as its cloud provider, tapping into the full range of Microsoft's cloud solutions to empower a connected and collaborative workforce, upgrade data centers, and increase analytics capabilities. Suncor also collaborates with Microsoft on innovation projects, drawing on expertise and opportunities from both organizations. We also continue to look at partnering with local companies in terms of artificial intelligence and analytics capability with our universities in Canada. So we're really interested in building that ecosystem as well as building the capability across Canada. We're a proud partner with AltaML, Spartan Controls, ATB, and TransAlta on applied data science internship we call AltaML Applied AI Lab. While Suncor is running its own digital transformation programs, the AI Lab will return additional value through continuous experimentation on machine learning use cases. We also collaborate with organizations such as Evoke Innovations, a fund that offers a unique approach to technology innovation, combining the pace and creativity of Silicon Valley startups with experience and insight of industry insiders. Another organization is Clean Resource Innovation Network, or CRIN, a pan-Canadian network focused on ensuring Canada's energy resources can sustainably be developed and integrated with our global energy supply, where one of the main themes of CRIN is digital technology. In addition, I'm also a proud member of Shikik, a nonprofit dedicated to engaging industry to build a supportive community where women in technology can thrive. This list is not meant to be exhaustive by any means, but indicative that our collective Canadian AI ecosystem is a big part of our journey. The Canadian AI ecosystem is vast, as can be seen by this very populated infographic on the right. So I'd like to close out with a question to the group here. What can we do together to move Canada from number 9 in the world to number 1 ranking in industrial AI? Let's strive to lead the global industrial digitalization with strategies focusing on AI and advanced analytics. Thank you very much.
Thank you very much, Mong. That was an excellent presentation. So this brings us to the end of the presentations in the session. We are now open for questions. We have about 15 minutes questions from the audience.
I can go first.
Sure, yeah, go.
Thank you everyone for the great presentations, really great talks. So I'll start with a question that was posed by Greg for Kalev, just because it was only in the panelist discussion. I'll read it out loud. So the question reads, do you have a problem in predictive analytics for rare events like failures? There can sometimes be a challenge with high FPs.
Yeah, actually, I mean, that was actually the biggest stumbling block and the biggest challenge we had. These events don't happen an awful lot, as you might imagine. Not every truck blows up, and so our data is not the cleanest data in the world either. There's a fair bit of missing data from all of our sensors, and as you might imagine, a mine data collection system is pretty widespread and has a very wide area to collect from. Regardless, what we've done is we worked with Python and actually built a simulation engine, very similar, Anoush, to what you did in your rare event issue, to fill in data and to actually create enough simulation events that match some of the patterns in a stochastic mode to enable the machine learning algorithms to then predict fairly successfully real events. And we also basically what we did was so the idea is here to prevent all kinds of catastrophic failures, and that's more important than having some nuisance false alarms. So that was actually the skewing. And so a missed opportunity is 90 times worse than the false predicting value. And so therefore was actually weighted 90 times higher. And as a result, I think that we got a pretty good predictive algorithm. But the problem with ML generally is that it's very brittle. So you get into conditions that, that you haven't seen before, and it won't predict them, number one. And number two, it's actually very confined. So the kind of truck that we were actually targeting, well, that prediction algorithm worked for that truck. The electrical systems on any other truck don't actually behave the same way, and we have a mixed fleet like Suncor has or anybody else has, and as a result, you'd have to do this over and over again for trucks. And as these systems are changed out to repair the faults or to repair the condition, those failures actually don't exhibit the same kind of pattern. So you have three conditions: a dynamic changing condition, few faults, and a very limited sort of scope. And I think that the real effort now is to sort of see how we can tool these into an automated method where we can scale across all the trucks, as opposed to doing it sort of in a bespoke way for one truck and one failure. But we have 90 of these projects going at the same time in the company. So, and they're not all failure predictions. They're all, it's a wide range of projects.
Awesome.
Yeah,
did you want to follow up on that, Greg, or?
No, that's good. I was just saying thank you.
Okay, sweet. I do have a question for the group. I mean, and anyone, if you guys have any opinions on it, please go ahead. So my question is, I mean, we saw 4 presentations that covered like a range of different sectors, and there was automation and prediction and all that kind of stuff. So my question is, have you been experiencing in your field any pushback from the individuals that work in the field in terms of out of concern for job loss? I work in AI/health, and we see that concern all the time, that people are worried, like, what am I going to go out of jobs and stuff like that? So do you experience that? And then if you do, what are some things that you or your company or organization does to sort of educate and strategize and like essentially with the core idea that this is all for the greater good, and what are some things that you're doing to make sure that this is done in an ethical way so people are not just like out of jobs?
I can take a first crack at that if you want, Delaram. I think so. I've applied AI in a range industries, and I find it depends on what you're doing and also the people in that industry. You know, how the reaction is going to be. And I think, let's say that we tend to try to find problems that are going to be useful, but actually, you know, a lot of these cases you look for things which are going to empower the people rather than replace them, or at least the problems that I've been looking at. And for example, one of the we were trying to figure out in a previous industry, you know, when fired heaters were about to break, right? And this is very difficult. It doesn't happen very often. Same, that's why I asked Kalev the question, right? But what we were able to do with these things, it turned out that the use case was that there was one person, a burner expert, who was in charge of monitoring and keeping track of 300 of these burners. This guy was really good. He could look at the data and tell you what was wrong with it. But now what he couldn't do was look at 300 burners 24/7, right? So what we're able to build for him, right, not to replace him, but to give him something, was something to find anomalies within those. There's about a dozen sensors on each one of those, and you know, pull those anomalies together so that when he comes in the morning, here's the top 6 things that you should look at, right? Here's, you know, these 6 burners are important, and here's the chunk of the data that you should look at, and then he would be able to look at that. So turn this huge problem into something more human-sized, and we found that made a huge difference with how people respond to us when you're able to do something like that.
If I can add something, a couple of our speakers really touched on a key point, which is the cultural aspects of change. And understanding that and managing that is absolutely critical. And so in our industry, engineers show a different response to workers on the floor. But fundamentally, you're fighting 2 things. You're fighting skepticism. Does this really work? But tied to that is a fear that that individual has a certain personal knowledge base, the experience that Greg was just talking about, which they think is critical to their employment. And they feel that they're going to be replaced. So the fundamental change has to be that you have to convince them that this is an enabling tool to actually make their life easier. So if they feel it benefits themselves personally, the fact that it benefits the company is actually secondary. Associated with that, at least in our industry, is a demographic that has people who learned the old-fashioned expensive way are all retiring if they've not already retired. So you have to ride the wave of new employees and these other cultural issues if you want to make this a successful transition.
Makes sense.
I'm happy to add to that as well. You know, I think the first part is acknowledging this is a natural human interaction, like it's going to be a human reaction for any change. Second, bringing together the culture change with the actual initiative or project work, I think is going to be key. The way we have resulted in our space is that we made sure that one of our values is curiosity and lifelong learning. Now, we can say all we want about the value itself, but we tied it with tools and capabilities that are easily accessible to our employees to be able to do the lifelong learning, right? So through an academy, through additional support materials that are built within our company. And to be honest, that behavior still will happen. And sometimes it is the relationship and understanding where do they see themselves going into the future, and how helping them understand that it's not about their current knowledge, it's about their attitude and their ability to be able to support the larger strategy.
And you know, I just to reinforce that, I think that that's absolutely crucial. And we've been very, very careful to bring, first of all, our teams are built not as IT teams. They're really guided by the actual business owner of that particular process at this point in time. And these folks not only own the result, they own the operation of the result. So, you know, it's sort of incumbent upon them to make sure that this thing is what they want and what they want to use. And I'll actually refer to chess players, and Gary Kasparov particularly, and you know, he had the infamous battle with IBM's Big Blue and lost. and he went through a grieving process. I think that was rather painful to watch. But chess players today actually can't beat a machine. But they also can't beat a machine and a very good player. And the machine can't beat a machine and a very good player. And it's actually that symbiotic relationship between what we build in AI and machine learning and all the other analytic tools, as well as our ability as humans to encompass all those brittle edges and understand the larger context that actually makes these things far more successful. So it's the combination of both. And Gary Kasparov really pointed that out. That was yeah. So there aren't very many very good chess players anymore. They're a good combination.
Mm-hmm. That makes sense.
Thank you very much. There's a question. Sorry. So there's a question from the audience. This is to Kalev. What was the decision-making process behind the decision to rank the false negative alerts as 90 times to 1 true alert? Was there any business?
Absolutely. The issue was that false positives are always a real problem in almost any kind of control system. And what it does is it promotes an operator's inability to distinguish between what's correct, in other words, the correct thing to take, and getting completely bored with being told that this was going to happen, and then ignoring it, of course, when it does. And so that's really really key. So what we've really done is really tuned down false positives, but even more made sure that the patterns that result in the actual occurrence are enforced. And so it is a bit of enforcement learning that was imposed upon this, but the imposition of that far exceeded the false positive pieces here, because again, the trust was built by those real positives. In other words, the actual real events that would have occurred had the machines gone back into the field. And so it was, and don't forget, it's a $4.5 million per year problem. You do want to actually encourage people to take a second look, at which they did when the algorithm is telling them to do so.
Thank you very much, Cal. We have about 3 minutes left. So I wanted to ask all of you one final question. What do you see as the biggest obstacles to using off-the-shelf AI algorithms? You know, there are three parallel tracks today at this conference. There is a track on fundamental science. Computer scientists are working on certain types of problems. They're developing new algorithms. They're using them on primarily image processing, video processing, etc. Some of you have identified specific problems that are relevant to your industries in terms of using these off-the-shelf algorithms that are developed by computer scientists. So to all of you, my question is, what are the biggest obstacles to using off-the-shelf AI algorithms, and how can AI researchers help you?
Well, I'll start perhaps and indicate that we do use off the shelf in terms of the underlying substrates and frameworks, whether it's Google or whether it's Microsoft. A lot of the methods are available to us from those arenas. The real problem is that data scientists need to know something about what they're data sciencing, right? And the people who are being data scienced, I'm using it as a verb, I'm sorry, need to know exactly sort of what that kind of analysis is, at least at some level. And so there has to be some marriage between the two that really ties them together and has that mutual understanding. And so you don't get that with a canned program. It's like saying, well, I'm going to put in SAP and turn it on tomorrow. It just, you know, SAP is a language. It's not actually a canned program in many ways. And so you have to be able to speak the language on both sides.
I would perfectly agree with Kalev. I think that we're all using off-the-shelf things, right? So nobody invents their own underlying algorithm. Usually that's not where the problems are, though. I think that for most of the problems that we're solving, we've got enough out there. The challenge is understanding the business problem, as Kalev is saying, well enough to really, get the sense of what it is that you're trying to solve and what answer is going to be acceptable. The next biggest thing is also to think about that data is going to be dirty. It needs to be mapped. It needs to be, there's a lot of stuff that needs to happen to it. So what all of this goes into, how do you structure what it is that you're going to be working on, including, and then what does your data pipeline look like? And really, if you've done all that right, the whether you're using something which is perfectly optimal or not at the at the underlying core tends to not be the thing that makes or breaks everything, right? So and I say that really loving algorithms, right? But it does, the place where these things fail is somewhere else, right? So those things are absolutely useful. The roadblock is, for some reason within the ML community, this rumor started, probably not within the ML community, but that you could just kind of throw data at stuff and then the answers will come out. So I don't know where that came from. It certainly doesn't, statistics doesn't work that way. Excel doesn't work that way. Neither does ML. So I think that making sure you do all this stuff right is the most important thing.
Yeah, I think
GP3 is at fault.
I think for me, off the shelf is a bit misleading as a term for this space, because there's always going to be some form of training configuration, unless it's a purely deterministic set of models behind the scenes, which I would not consider as AI or advanced. And there's model management, sustainability to be considered, model drift. And from a Suncor perspective and my team perspective, I have an extra hurdle of being an integrated company. So multiple different businesses, from retail to wind to mining to in situ. And so there are so many tools to consider. So many off-the-shelf tools are standalone. They don't always work well together. And not surprisingly so, because they come from different companies. So after a while, how do you integrate the value across the chain? Because optimization or prediction for one business may not be the best value for the overall organization if you combine that with retail, for example. So those are the things we definitely work around and have to consider as an integrated company.
If I can add to that, I would totally agree with everything that was said, and really say that the biggest thing we need is sort of enterprise level integration of all these tools in a way where you have traceability, where you have the ability to check things. And if we look at, say, ERP level financial systems, we know what messes those have been when people try to implement them, and the difficulty to customize them for a particular enterprise. Same thing's true here. How do you bring all of this together in a way that is manageable and sustainable?
Thank you very much, Anoush. So we're sort of out of time here. That brings us to the end of this session. I would like to thank our 4 speakers one more time. I don't know how to do that virtually, but maybe we can just clap our hands. You can't see the audience. For the audience, there is a poster session starting right now. Please go check the posters out. After the poster session, there is going to be a panel discussion starting just after 11 o'clock. So please hang out on Gather platform. If you find the speakers there, you can perhaps ask them more questions if you have any more. All right, thank you very much. It was a pleasure chairing this session.